Hello everyone, my name is Sergey, and today I'd like to talk about modern approach to search and recommendation systems, and highlight some of the scaling challenges and how they can be addressed based on my hands-on experience. Over the years, I've led work on video search, personalized video recommendations, and product search at companies like Yandex and Microsoft. This presentation is very short, so I'll focus only on the most fundamental problems and solutions, and each of these topics deserves a separate deep dive. This talk covers the core ideas behind ML-powered search and recommendation systems, from why they matter to how they are built, ranked, and scaled. We'll look at key models, system design practices, and recent trends shaping the future of recommender technologies. Let's dive in. Recommender systems are essential for helping users navigate huge catalogs of content and products. They reduce information overload and improve the user experience by surfacing relevant items. They also drive key business metrics, more clicks, purchases, and return visits, and help optimize for long-term value using technologies like reinforcement learning. And the impact is huge. Even older public statistics show this very clearly. About 70% of YouTube views, 35% of Amazon purchases, and 80% of everything watched on Netflix come directly from recommendation systems. Those systems aren't just helpful, they are essential to how modern platform works. And before we build or improve a recommendation or search system, we need a clear way to measure success. And these are two main types of metrics, offline and online. Offline metrics are fast and safe. We compute them without touching real users. They are based on labeled data or evaluator guidelines, and they are great for quick iteration. But they are often don't correlate well with real business goals. And online metrics are different. They come directly from user behavior, usually through A/B tests. They are accurate and reflect business impact, but they take time and carry some risk because they affect real traffic. Both types matter. Offline metrics help us move quickly, while online metrics tell us what truly works. And also, when evaluating recommendation systems, we often look at two types of goals, short term and long term. Short term is based on immediate user actions, things like clicks, dwell time, or purchases. These are easy to track and give us quick feedback. But if we focus only on them, we risk overfitting to short term interests and ignoring real user value. So, long term is about user satisfaction over time. They are harder to measure, but they better reflect the true value, such as retention, subscription continuation, or content diversity. These metrics encourage exploration and help build loyal users. In short, short term metrics are helpful, but long term metrics are what really drive sustainable success. And let's take a look at the big picture. This is high level architecture of a typical machine learning powered recommendation system. At the top, we have the serving layer, which is the heart of real time response, and it includes candidate generation, which retrieves a manageable set of potentially relevant items, feature generation, which builds features using user query and item data, and models and business roles, where ranking models score candidates and business logic handles diversity exploration and cold start cases. These are the blocks we will focus for the rest of the presentation: candidate generation and ranking. And now let's zoom out for a second and look at the full loop. At the input, we have user data, queries, items, and real-time events coming through a data processor. That's how context and behavior enter the system. Equally important is the login infrastructure. Everything users do, clicks, scrolls, dwell time, is logged and sent into offline pipelines. Why is that important? Because we rely on this data for training, evaluation, and experimentation. If we log incorrectly, we'll train on biased or broken labels, which directly hurts system quality. In the training pipeline, we apply labeling strategies. some manual, some assisted by LLMs, and train our models using full retraining or active learning or online updates. At the bottom, we measure success. That includes both offline metrics like AUG and NDCG and online metrics like CTR, time spent, and revenue. The loop is closed by using these metrics to guide further model improvements. So again, in this talk, we'll go deeper into the candidate generation and ranking layers, but keep in mind, the rest of this architecture is equally critical to building a successful system. And to make recommendations at scale, we use a multi-stage retrieval and ranking funnel. The idea is simple. We start with millions or even billions of items and progressively narrow them down to the top 50 that we actually show to the user. Let's walk through each stage. We begin with user profile and query understanding. These give us context. Then we move into candidate generation. This stage focuses on high recall. We want to gather as many relevant items as possible. The goal here is to cast a wide net and collect around 10K items. We also factor in things like diversity, freshness, and popularity. Next is pre-ranking. At this point, we filter down from 10K to roughly 1K items using lightweight models. Often it's gradient boosted decision trees or fast neural networks. We are still optimizing for recall and diversity also here, but the computation needs to be fast. In L2 and L3 layers, we do heavy lifting. These stages use complex models like deep neural networks or transformers. We want to evaluate each of those 1K candidates in depth and select the top 50. The key metrics here is NDCG, which reflect ranking quality and relevance. And finally, there is a re-ranking stage where we apply business rules, for example, to increase category diversity or boost new items or ensure legal or policy compliance and so on. And what's powerful about this funnel is that it balances performance and efficiency. We use simple models early for speed and heavy models later for accuracy. So system stays fast but delivers high quality results. Let's look at candidate generation stage. Once we have understood the query and user profile, the first step in the pipeline is candidate generation. And the goal here is to select a small manageable set, typically thousands of items, from a catalog that may contain millions or even billions. And this step needs to be fast, provide high recall, and maintain diversity. These are several approaches to do this efficiently. First, we have ANN, or approximate nearest neighbor search, which finds the closest items in embedding space. Popular libraries include FAIS from Meta and Scan from Google, with fast algorithms like HNSV. ANN relies on good embeddings, which we can get from collaborative filtering like LS, which is fast but struggles with cold starts, and content-based models such as two-tower architectures based on DSSM or BERT. In search-based systems, we often use inverted index, which maps query terms to documents. This scales extremely well to trillions of items, thanks to techniques like term sharding and BM25-based ranking. Finally, don't underestimate heuristics. Simple rule-based filters like popularity, recency, or user subscriptions are still widely used, especially when latency matters. So the takeaway here sounds like there is no one size fits all solution. Most production systems combine multiple methods, NN, heuristics, and inverted index, to balance performance, coverage, and latency. Let's dive into inverted index. Inverted index is one of the simplest and most scalable ways to generate candidates. Offline, we pre-process the entire catalog, extract all of the words, store where they appear, and build an index. We can also use unigrams, bigrams, or trigrams, and then shard the index across machines for scale. Online, it's very straightforward. We take the query words, look them up in the index, fetch the matching documents, and return the top results, usually the top 1K, to pass into the ranking stage. This approach is fast, reliable, and works extremely well for search style candidate retrieval. Another popular way to generate candidates is ANN index. ANN based candidate generation is how we find similar items using embeddings. Offline, we compute embeddings for every item, usually with ALS or two-tower model, and then build an HNSV index. HNSV is a multi-layer graph structure that lets us search nearest neighbors extremely fast. We also share the index so it can scale across many machines. Online, the flow is simple. We compute an embedding for the user or the query, search the HNSV index for the closest vector, and collect the top candidates, usually around the top 1000. That will go to the ranking stage. Once we generated a list of candidate items, the next step is to rank them, to decide what to show and in what order. And the goal of ranking is to sort the candidates by relevance and other objectives like diversity or conversion potential. These are two broad types of optimization goals. Short-term metrics like NDCG, MRR, or P at K, these are widely used in industry and are based on offline judgments and historical user behavior. And long-term metrics, which are still an active research area. These includes approach like reinforcement learning and sequence models that aim to optimize for lifetime value or sustained engagement. Let's look at the main approach which we can use. Gradient boosted decision trees models such as XGBoost or LightGBM are very popular in production. They are fast, interpretable, and work well on structured features. They are often used at the final ranking layer. On the other hand, deep neural networks like DSSM, BERT, and other transform-based models can model more complex interactions and are commonly used in upstream stages like ANN or as feature generators for gradient boosting. Of course, ranking isn't easy, it comes with several challenges. Let's look at them. Biases, such as label and position bias, come from implicit feedback like clicks. The cold start problem, when we lack history for new users or items. The classic trade-off between relevance and diversity. And another trade-off, exploration versus exploitation. Do we show what's already working, or do we help users discover new things? Another challenge is interpretability. It's also concern. Gradient boosting is easier to explain, while deep neural networks often behave like a black box. Another challenge is privacy. Privacy is becoming more important. Many teams are exploring federated learning to train models without centralizing sensitive data. And finally, latency. Deep models can be heavy, so we need techniques like distillation or caching to keep the system responsive. So in practice, teams often combine these methods using neural networks for representation and gradient boosting for final scoring to get the best of both worlds. And this slide shows a typical architecture used for ranking in model recommendation systems. We start on the left with input features. These include user features like demographics or user behavior, item features such as price, popularity, or category, interaction features, for example, how often the user has interacted with similar items, contextual signal like time of the day or device type, and often a score from a lightweight two-tower neural network that helps pre-rank items. These features are then passed to a set of gradient-boosted decision trees models. One model estimates the probability of relevance, another predicts the probability that the user will click if item is shown, and a third estimates the conversion rate if user clicks. The scores can be combined into a final ranking score depending on business goals like engagement or revenue. In more advanced pipelines, we may also use a multitask deep neural network, shown here at the bottom. This network is trained to predict the same targets. relevance, clicks, and conversions, but it can model more complex relationship and input combinations. Finally, once we have a rank list, we apply re-ranking logic. This includes promoting diversity to avoid showing too much of the same content, introducing exploration to test new or less known items, and applying business rules, for example, to boost sponsor content or ensure policy compliance. In production, this architecture is often hybrid. The deep neural network might be used offline or upstream, and gradient boosting remains the final model for online serving due to its speed and interpretability. Let's now compare two of the most common approaches to ranking: gradient boosted decision trees and deep neural networks. Starting with gradient boosting on the left, these models are widely used in production, especially for the final ranking stage. They work very well on structured data and easy to interpret, and support fast training and A/B testing. They are also great for small to medium data sets and have low latency, making them ideal for high throughput environments. But gradient boosting also has its limitations. It struggles to model complex iterations. Uh, it doesn't handle sequences or multimodal input as well. So they also don't scale as effectively on a large data sets compared to neural networks. Now moving to deep neural networks on the right. These are seeing increased adoption in both research and in industry. DNNs can capture both explicit and implicit feature interactions, handle embeddings for high cardinality features, and enable end-to-end training on sequence like user history. They also support multitasking and transfer learning, and scale better with more data. However, deep networks also bring their own set of challenges. They are computationally expensive, harder to debug, and less interpretable. They can suffer from issues like bias, fairness, and even hallucinations, and they tend to be sensitive to noise or small changes in input. Because of these trade offs, many real world systems adopt a hybrid approach, using neural network upstream for candidate generation or feature extraction, and gradient boosting for final ranking to balance performance and efficiency. Mm. When building large-scale neural networks for recommendations, performance is important, but scalability and efficiency are critical. This slide outlines some of the key design principles that help us get both. First, we have late fusion and B encoder architectures. Instead of scoring user item pairs in real time, we with a single tower, we split them into two: user tower, which runs online, and item tower, which pre-computed offline. This can lead to over 100 times speed up while preserving more than 80% of total profit in some systems. And next is contrastive learning. This trains the model to distinguish between positive and hard negative examples using losses like info NCE or anti-Zend, and the goal is to produce embedding vectors that are compatible with fast dot product retrieval. In some cases, teams report up to plus 100% profit uplift in retrieval performance. Another common challenge at scale is embedding size. So we apply compression techniques like hashing, quantization, or distillation to keep memory and latency in check. Another critical aspect is bias correction, including popularity bias, position bias, and feedback loops. And one trick here is to add a context-aware tower during training, but drop it at the inference time. And we also apply hard negative mining to make training more meaningful. Instead of using random negatives, we sample negatives that are hard for the model to distinguish, and this makes the learning signal much stronger. Then there is multi-signal learning. Our models often consume inputs from multiple modalities: text, images, tabular data, and from different domains like search, queries, watch history, or cart activity. And finally, sequential modeling is crucial. We use transformer-based encoders to capture the temporal aspects of user behavior, feeding in recent events first to predict what comes next. These principles together make it possible to run deep learning at massive scale in production recommendation systems and without sacrificing speed and quality. Uh, Now let's talk about why scaling recommender system is much harder than scaling LLMs or vision models. It's more about quality scaling. On the left, we see that LLMs and computer vision models scale extremely well. They take in long sequences like text or pixels and benefit from dense labels and strong supervision and have powerful pre-training tasks like next token prediction. They use deep transformer architectures and are often latency tolerant. We don't mind waiting for a few seconds for response here. In these domains, scaling almost always improves quality, and scaling laws are well established. Now, contrast that with recommender system on the right. We deal with massive embedding tables with billions of users and item IDs. And our models are often tiny multi-layer perceptrons, and they must respond in milliseconds. So we are under heavy latency constraints. Our data is based on short, spare behavior sequences, just a few clicks or skips, and feedback is implicit. And we don't have a universal self-supervised pre-training task like LLMs do. And also, no clear scaling law exists here. As we grow models, we quickly run into bias, noise, and diminishing returns. And the key takeaways is in the box at the bottom, we say that recommender systems hit unique scaling limits, including latency, implicit feedback, massive embeddings, and domain-specific biases. These can't just be solved by making models deeper or wider. We need domain-specific innovations. And now let's look at the main trends in modern recommender systems. First, we see a shift from classic gradient boosted decision trees models to deep neural networks. Second, many companies move to multi-stage pipelines, fast retrieval first, and a stronger model for ranking next. LLMs are becoming part of the task of the stack too. They help interpret embeddings and generate responses. And we also see big progress in model architectures and scaling laws, especially for large recommendation systems. Sequence models are improving long-term predictions, and graph neural networks help understand the relationship between user and items. And finally, reinforcement learning is gaining adoption as a way to optimize long-term value, not just clicks. Overall, the field is moving toward bigger models, better personalization, and more long-term reasoning. That brings us to the end of the presentation. Thank you so much for your attention. We covered the fundamentals of ML-powered search and recommender systems, explored key architectural components, and looked at challenges in scaling. I hope this gave you a useful foundation and maybe even spark ideas you'd like to explore further. Thank you.